Welcome to AI for Good, the leading, action-oriented, global and inclusive United Nations platform on AI. Organized by the International Telecommunication Union, the United Nations Agency for Digital Technologies, in partnership with 40+ UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to identify innovative applications, build skills and standards, and advance partnerships to solve global challenges. In today's AI for Good event, we are counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished facilitators and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hi everyone, today's speaker is Jinyi Huang, who is a quantum developer advocate for Qiskit at IBM Quantum. He is passionate about making quantum computing more accessible to the public, and over the past few years, he has played a large role in planning major events, such as the IBM Quantum Challenges and the Qiskit Global Summer School, as well as managing the Qiskit Advocate Program, which connects advocates with IBM experts, ultimately leading to the development of valuable research projects and kickstarting some of their careers. Jinyi will be discussing how to teach quantum and the tools and strategies that work. Let's please welcome him.
Thank you for the introduction. So let me try to share the screen. Right, hope that works. All right, so hopefully you can see my full screen. Okay, so that's good. Right, so today I'm trying to talk to you about how to teach quantum and the tools and strategies that work. As Jenny tell you a bit more about myself, so I just want to give a bit more detail. So I'm based in Valencia in Spain, and in my current role, there's two parts. Half of my role is I'm based in Europe and Middle East, Middle East and Africa region. So I work with our clients and community, managing and designing different educational programs. And then the other side of my role is I'm a global lead of coding challenges. So that means I oversee the execution and planning of these flagship coding challenges event like IBM Quantum Challenge, Qiskit Global Summer School, and Quantum Developer Conference. And previously, I was the APAC lead for workforce and education. And as Jenny mentioned, I also managed the Qiskit Advocate Program. And I used to contribute to Qiskit, and I was the documentation maintainer. And before I joined IBM, I did my graduate research on topological superconductivity experiments in Singapore. So today I'm really excited to use my experience for the last few years working on quantum education to share some of the tips and tricks that I learned and also have a discussion with you. So recently I taught a class for beginners in quantum computer, and they have a mixed background. There's people for starting undergraduate, some are graduate students that are doing research, and there's some working professionals that are trying to see how they can use quantum computing in their work. And then I have a lot of different feedbacks. So I was trying to teach people focus on more on the code, less on theory. And still some people think they want to see much more programming than theory. While on the other hand, some people that are maybe more from math and physics background, they feel that I covered too many concepts that are superficial and not in depth. While people that are in company, they still don't see how they can apply the concept that I taught them and how to apply it to the company. So as you can see, really teaching quantum is really difficult. Even after I work in IBM Quantum on this educational role for 5 years, I still face daily challenges like this. So, so just to start, I want to see how many of you are actually having problems learning and also teaching quantum. And also I want to make this talk a bit more interactive. So we're going to jump onto a Slido on website to really see how you are going to, what kind of challenges you face as you're teaching or learning quantum computing. And so you can scan this QR code or go to slido.com and put this code. And then you can choose the options that where which kind of things that you find is the most difficult when you're teaching quantum. So I'll give you yeah, maybe some seconds, and let's see how you can join. Hopefully people don't have problem joining this Slido. So okay, there's something nice. So there's a few. These are the common things that I find is very hard. For example, one that is really often overhyped and oversimplified. You see so many news on the internet, and that people will tend to explain like quantum it is like the most amazing thing in the world. Or there's also abstract math, strange languages, and familiar models that people really don't know how to explain. And this concept are often very counterintuitive. It's something that you don't really see in your daily life, and therefore it's very hard to make your learners very like relate to your daily life and trying to understand based on your experience. And also because this field is really, really like popular now, it's often on the news, as I mentioned, and people are really trying to get into a field understanding how it works. And therefore, there's people coming from very different background. They might be students that are learning and seeing this is very promising, or maybe people are already learning, working, and they're trying to jump into this field. And so people have different background and also different kind of goal in mind when they are into quantum. And so that really adds to a lot of challenges as well. And so we're seeing more and more posts. So I think we can keep it for another 10 seconds or so, and then see. So far it seems like the math is the most difficult part for many people. And then second is the typing. And then third is the learning from different background. So yeah, then let me jump back to the slide. So these are the 4 reasons that I listed in the options, and as already covered, because these are really counterintuitive concepts that you cannot show experience from a daily life, and math to explain that is often very abstract and difficult, and learn have different background, so then you have to cater to them. And because there's so many hype around that people may also have a different expectation, maybe a over expectation of what the technology can do. And then also in the medias, maybe the explanation for many of these concepts are overly simplified. And as we try to teach quantum, for example, my recent experience of teaching this to beginners, sometimes you want to make things a bit lower the barrier of entry, making it a bit more accessible. But then sometimes actually that will leave the learner even more lost than they can be. So one way to make the understanding easier, teaching to lower the barrier entries would be like using some analogy. But if you use some analogy overly and simplify things that beyond what you are trying to do, that you can actually leave like without the mathematical rigor that you're trying to explain, it might actually confuse the learner even more than clarify. And also, as I explained, that these concepts are not really intuitive, so often you should rely on math to really build intuition. And if you skip through the math, then the learner will feel like this is a black box and it's like magic. They don't actually know how things are working. And I was trying to do this as well with the class I was teaching. I wanted to really skip the math and jump into coding, jump into Qiskit, showing people how things work. But that didn't really help because without a mathematical intuition, it's very hard for them to really see what is actually going on. So these are not bad ideas per se, they're just not complete. So if you are relying on one of these strategies too much, then you actually will really make your learner confused and feeling that they don't get anything, they cannot really progress to the next step. So from thinking about the different needs of our learners, so I was preparing for this presentation, I think it through based on my experience of teaching different people, running hackathons and also coding challenges. These are 5 things that I feel that people really need in order to really progress and learn more about quantum. First, as we show already, there's people from different backgrounds. So they might need tailored instructions from different background or different stages of life or different like preference of learning style. And also the concept are often very complex, so you want to really layer your explanations, slowly skewing to more complex. And also to make this complex idea easier to digest, you added about more engagement, interactivity, and play. And it's also because people are very different, they might even apart from the background, but also could be different way of thinking, different way of doing things. They also want to have different ways of explaining things. And even for the same person, maybe you want to see things in a different way to enhance your understanding. And as I emphasized a few times, to building the mathematical intuition to explain the quantum phenomenon is really crucial to really understanding in depth. So whether you're teaching a high school student or a graduate student, these needs are not going anywhere. They're just going to scale in complexity if you're teaching someone that is a bit more advanced. So based on this, while I'm preparing for this presentation, I come up with these 5 principles that will help you to teach quantum computing more effectively. And it's corresponding to these 5 different needs. And to help you to remember these 5 principles easier, I make up this leaps principle, like quantum leap, like quantum jump. So L is standing for learner first. You should understand your learner, knowing who they are, and therefore you can tailor the way you are teaching. And E is for example and scaffolding to build up step by step explaining it to build up the complexity. And A is for active engagement. And P is to present in multiple ways. And S is show the math. So for the rest of the presentation, I'm going to go through these principles one by one and also showing you some examples of how we could do that. And also some real example that I have done in my work to show you how we are applying this kind of principle in real life. So principle 1 is learner first. So this is really the most important. Understanding where your learner, their background, the stages, and what they're trying to do, and adapt your approach accordingly. And the background could be whether they're a high school student, undergraduate, they're student working, or maybe they're even retired. And another aspect of the background is maybe they know physics, chemistry, or they have studied computer science, or engineering, or even social sciences. And then stages means where they are in learning quantum computing. Are they completely new to this concept? Are they just started? Or maybe they are very advanced? And for different stages, then you should also cater differently. And in terms of goals, there are people coming into this field or attending the talks that you are given for different reasons. Some might just hear it from the news and want to find out more about it. Some may be taking this as a hobby, want to have fun and understanding, just playing with the code and doing different cool things. Or maybe someone is maybe a student or someone want to find a job in the quantum industry. So they really want to be able to dig very deep to apply this and get a job. Or maybe someone is already working, but then they want to apply quantum to the work that they are already doing, or their company is asking them to explore how can using quantum computing to help their business. Or someone a researcher and they want to apply quantum to their research project. So depending on all these different factors, understanding your learner, what their background is, which stage they are, and what their goal is, will really help you to cater different ways of teaching. So let's jump back to the Slido, and we'll see for you what is the learner that you are teaching. Are they? And I'm only taking one aspect of it. Otherwise, I have to do multiple voting. But I'm not just thinking about which stages. I mean, which level are they starting, or working, or retiring, or maybe you're not teaching. You're tuning in for this talk just for listening, trying to see how we are doing different things. So let's see how it is. So you can go back to the Slido, scanning the code, and putting the code. Hopefully, if you use the same link, it should still work. So let's see if there's any, okay, let's move. Doing training. So working professional right now is the highest. Undergraduate. Okay, some people are not teaching. Okay. So far, it seems like working professional is the most popular, which is quite surprising to me. And then followed by undergraduate and grad students. So you can really see that there's a lot of people are trying to switch their career or trying to apply quantum into their company. Okay.
There's a question in the chat. So
Okay.
in designing quantum curriculum for diverse learner profiles, from high school to professionals, how do you reconcile content depth with accessibility without diluting the concepts too much?
Yeah, so that is really a challenge. So I'm here now, I'm saying that trying to get to learn your learners, and that will be a first step. And it's most likely a mix of different people. And even if they're same, like they're all undergraduate students, they might be from different department, or maybe they are all working and they might be different principal, or maybe they're same like background in terms of like their physics or chemistry, they might be in different stages of their life, or maybe they already learn quantum. So that is a really great question, which I will cover a little bit later. How to cater to most of these people in the same kind of courses or same kind of like engagement or talk is actually very challenging, which is what I'm trying to figure out. And you may not be able to do a perfect job. Maybe sometimes what is better is to, if you can maybe like be clear about the thing you're offering is for certain people. Maybe you specify the preference of the background or people to have, then you can maybe cater to them. But for sometimes like the IBM Quantum Challenge, which I will show you example later, we are running event for thousands of people. So that is very hard to target to only a specific type of people. And there you can design multiple different things that then cater to different people from different background or different level. And maybe some people can do some of that thing. And some people, if they're advanced or they're trying hard, they can take more. So I'll cover a bit more in later. But that's a very good question. Okay, so now switch back to the presentation. So it's good to see that actually a lot of people are trying like teaching to working professional, which I was not expecting. I was expecting to have more like undergraduate students. So really clearly see that there's a lot of people are really trying to get into the quantum field, which is really exciting to see. And just as I show you, there are many things that you can try to find out about learners. Like you can use the online poll that I just used, like Slido, or maybe if you're doing a like in-person event, you can do a show of hands, ask people your background or your or certain basic knowledge. Uh, Even better would be if you're doing some event that you can do a registration survey and put a few questions that to find out what's your level or understanding of quantum computing, what's your background, are you starting, are you working, what do you want to get most out of these events? I think knowing this would be really the fundamental basis of how you're going to design the talk or workshop or hackathon or anything. That is really your source of truth that you need to stick to. So that's why it's put in the principle one, number one. And then principle number two is examples and scaffolding, because the concepts are so complex, really building layer by layer, bringing down the complex topics into like progressive steps that are with meaningful examples so that they can understand, okay, from this step to that step, I can get it. And then they feel like they have this solid foundation to move on. That's very important. And I give you some basic example. For example, how do you explain Hadamard gate to someone that is new to quantum computing? And the emphasis here is new. So this is a bad example, what not to do. You could explain, and I have seen people doing this, especially if you are going to some physics department of a university and then you listen to a professor talking about this kind of thing, then they might talk these languages. The Hadamard gate transforms a qubit from a computational basis into a superposition state by applying a unitary matrix, whatever. In this one sentence, almost every single word could be something that people don't understand if someone is new to quantum. What is a gate? What is a qubit? What are the computational spaces? What is superposition and what is unitary? And what is a matrix? So that could contain a lot of concept that immediately lose your learner. So one example that we could take would be, which is pretty typical, that you start with something that your learner already know, or at least something basic that you can easily explain, and they feel that they can grasp this concept, and then build on top of that. So you can start with like classical bit, you say like bit can be 0 or 1, and then you introduce a concept of qubit that could be, or maybe sometimes you do hand waving, it can be 0 and 1 at the same time. It will be a mix of different things, superposition, and then you can talk about gates, what are the classical gates in like classical circuitry, and then quantum, you have something similar. And then you can introduce the Hadamard gates. And to make a bit more rigor, you can work on the math. And then with all this step by step, hopefully the understanding of, for someone new to quantum computing, it can still help them to understand this concept about Hadamard gates. And as promised, I will give you a real world example. So last year we have IBM Quantum Challenge 2024. And our internal goal is to teach people how to run utility scale experiment on real hardware. So utility scale is something we call a problem or experiment that is big enough that a classical computer cannot simulate using brute force simulation. So usually, typically, this kind of problem we use maybe a circuit that is 50 qubits or 100 qubits. So that's what we are trying to do. And obviously, this is a very advanced topic. And as I explained, we have thousands of people joining IBM Quantum Challenge. People have all backgrounds, all different levels. And the way we approach that is, in IBM Quantum Challenge, we have multiple Jupyter Notebook lab exercises. And so we build within the each lab, in the selection lab, each lab is increasing in complexity, and each lab is adding more and more concept. And within each lab itself, we also use this scaffolding concept to really build on top, and with multiple exercises, making sure people get the concept covered before they can move on, so that they know they have done and learned something. So this is the example that I'm showing you. So in lab 0, we did a setup, help people to set up the developer environment, installing Qiskit and IBM Quantum accounts. Very basic, but we also want to make sure whoever is new to this, they will have a space and set everything up before they get started. And lab 1 is to help people to understand what is quantum circuit and what are Qiskit primitives, how do you compose circuit using Qiskit. And lab 2s are transpilation, and that is a concept that when you create an ideal circuit on Qiskit, you need to translate to something that the hardware can run based on the topology of the one hardware and also the instructions. So we explain what is a transpiler, what are different stages of transpiler, and how you can build your own transpiler. And all these concepts covered in lab 0, lab 1, and lab 2 is going to be used later. So we jump forward to lab 4, which is the final one, is a variational quantum classifier. Is the algorithm for machine learning using variational quantum algorithms. And so we just show people first what is this algorithm, how you can use the algorithm on a simulator on your laptop. And then we explain what are the impact of noise in quantum computers and how you can mitigate these errors and noise using error mitigation techniques. And then we show them how you can use a small example, 5 qubits, variational quantum classifier on a real hardware. And even there, people have to apply everything they learned before. They need to know how to make the circuit, how to run it using a sampler, and need to use the error mitigation techniques. And then at the end, we have a bonus lab for people that completed everything and they feel confident. We give them extra hardware access, extra resources, and they will have to tackle this 50 qubit VQC. And there they have to consider something more advanced. How do we encode the data more efficiently that is mapped to the hardware? And also how to use more advanced error mitigation techniques. Is there more questions?
Yes. So how do you manage the transition from conceptual to computational understanding? Example, moving from describing a quantum state to programming it in a tool like Qiskit.
Okay. That's something that I also will cover in later in the principle about like showing things in multiple ways. So I think that there's many different ways that you could do that. You could do it in like first you explain a concept, like maybe you explain the analogy, showing people to understand. The first important thing is to make people to feel that they can understand. And then maybe you can rely on the math to draw this and then the coding. Or in Qiskit, when you explain some concept, right? When you quantum computing, you can often into a maybe an algorithm or something that we end up with a circuit. And circuit maybe is a common language that you can connect from your theory to like coding, because from the algorithm you demand certain kind of step that you need to do that can be described in the form of circuit. And then you can then go to the coding in Qiskit or Python. You say like we can construct a circuit using Qiskit in this way and then execute it to the hardware. So that might be one way that you can think about how to connect those. But there's multiple ways you can do that. It might be that you don't connect them like this sequentially, but you just show same concept in multiple ways, and maybe they will feel like they form this more complete understanding, even without a like very direct transition. But it also depends on the concept, I would say. Depends on what we are trying to teach. So just to show that we did have some people who managed to do this within the 10 days that we run this event and run this 50 qubit utility scale experiment, which is really close to cutting edge research experiment. So that was really exciting for us. Okay, moving on to principle 3, active engagement. Really, I think if you look at how children learn, really they learn by playing, and I think the same principle apply to everyone. And I'm actually doing the same kind of things. During this talk itself, I'm doing some polls, asking questions and things, because when you are learning in more interactive way, you really deepen your understanding and maybe paying more attention. So you can use something like games or quizzes or live demos, that different kind of thing that you can deepen your involvement. And I show you some example here, and I also show you some live demo to show you some of this example. So games are very good, especially for people that are new to quantum computers. Or maybe for younger audience, because for them, all you need is really to catch their imagination. They would just need to be maybe inspired or to feel that this is something cool or exciting. Then if they get that part, that might be good enough for them to stay curious and still learning. That would be really good. So that's what games good for. And quizzes, if you're teaching something like a course or some workshops, so just to make things a bit more like dynamic, or you want to test understanding of some basic theoretical concept or find out how your audience is doing, that is really good. You can use built-in polls of the video conferencing apps, Zoom, Microsoft Teams, or using Slido or Kahoot, like the Slido I'm using. So that would be really good for you to really make sure people are following. And then demos, I'm going to show you one example is Quantum Composer, from IBM Quantum website. It's a visual composer that you can build circuit and show how the circuit it changes the state and things like that. It's pretty good. And of course, code demo is also very useful later when you have more advanced topics. So I will talk about one quantum game, which is Q-Pong, which is something that I made a few years ago, even before I joined IBM. And basically, it is a Pong game, which is a very classic video game from 1970s, with two paddles and a ball. Hopefully, many of you knows this game. But what is different here is On the left hand, you have the classical computer like the usual, but on the right hand side, you have a paddle that is controlled by quantum circuit. And the location or position of the paddle is determined by the quantum state of the quantum circuit you compose below. And this is a very good way to introduce something very basic concept and like what is a quantum circuit and what is superposition and what is measurement. And that is very good for beginners. So I can show you. This is a version that I built, the original version on Python that actually uses Qiskit. And later I built another version that is playable on browser. And so it's easier for people to try it out. So let's see. Hopefully you can see this one. Let me set. So you can go this link or you search for coupon, maybe you find this one. I can show you how this game looks like. So it's very much the same as the one version I show on slide, but in just a slightly more retro feel of it. And so below you still have this 3-qubit composer. And on the right-hand side, as I mentioned, the paddle is determined by the quantum state and each of the position corresponding to this basis state from 000 to 111. So right now the quantum circuit is empty. So the state is 000 and nothing is happening. So when I usually teach, I always tell people, okay, you can do X gate, which is like classical. You can just flip the beats and you can change the position. But what is cool is that you can also do Hadamard gates, which is a superposition where you can actually make the paddle twice as big. But of course, it's not really true. Okay, I already lost. Because when the ball is actually coming to the paddle, you would trigger measurement and collapse the paddle. Okay, now we are lucky and we get this part. But you actually collapse and only one of the position is finally measured. So this is a really cool way by a very simple game. People by playing it already can get maybe one of the most important concept of quantum computing, superposition, and also the collapse of quantum like wave function and quantum state while doing this. So this is something that I often use when I'm teaching to beginners. Okay.
Question in chat.
Yeah.
So have you found some quantum concepts like superposition or entanglement are more easily taught through play? Can play also be used for assessment?
And play for assessment. What does it mean? Like to assess people's knowledge?
Yeah, I think maybe perhaps like do these games help facilitate a person's assessment of how well they know the concept?
Okay, yeah. I mean, okay. If you can beat this game, I guess you kind of have to understand the superposition how it works. So I think that could be, and depending on the game. So there's another game which I am not going to demo here, which is called Qiskit Blocks. It is a Minecraft kind of game, and inside the game, I work with my colleagues. I have escape rooms, and each of the room have like circuit puzzles. So on the wall, you can see some kind of state that you are asked to create, and your quantum circuit and visualization. So that will, I think that is better than coupon. It's more advanced. That you have to understand how the quantum circuit works, and to create a quantum circuit that reaches the quantum state to actually unlock the room and move to a next one. So some, depending on the game, some might be good for just giving the whole, like coupon, I think is good for like the showing to like the kids or like someone completely new to this and to just get attention. Qiskit block may be a bit more advanced and help people to really actually learn more stuff beyond to just like the basic. And there's also other games that I show here. Quantum Flight Trap is also very, you can search on it. It's a very well-established game that teach you quantum mechanics by a puzzle using some optical puzzles. And Quantum Odyssey is a game that you can even buy on Steam. That is maybe the only quantum game that you can do by this. So depending on your purpose, again, back to the learners, depending on where your audience is, what they're trying to do, or what you're trying to teach them to what stages, it might be useful for games, and different game might be useful for different people. Okay. And then the second thing I'll show is the composer, which is also very good for people that are new, and also maybe people that are not so knowledgeable in coding. So before jumping to Qiskit, you can show them already using the quantum composer how they can just construct circuit without being like getting startled or intimidated by the code. So the composer we basically have these circuits, and then below there's also a lot of visualization tools. On the right hand side, you have some panel that this circuit generated, and you can even create Qiskit code by this. So I can, for example, teach, for example, Hadamard gates or superposition or entanglement using this. So let me just remove some qubits. So right now there's a 2-qubit circuit, and you can see that there's nothing. And in Qiskit or in IBM Quantum Composer, we initialize in 0. So we can see that in Q-sphere, which is a visualization we use for multiple qubits, is 0, 0. State vector is 0, 0. Probability is 0, 0. We haven't shown anything, so by default doesn't show. But let's say if I put a X gate, you will switch to 0, 1, 0, 1, 100% 0, 1. So that is just like classical. But if you do Hadamard gate, then you do a superposition of 0, 1 and 1, 0. And very often I will teach this one as well with entanglement CNOT gates, and that is called Bell state. Then you have entanglement of 0, 0 and 1, 1. So this really helps you to, for you as a teaching tool, and also for the learner as something they learn and play themselves. They can drag and drop, and they can see the visualization. And even cooler is you can actually run it on hardware. So you can actually choose a real quantum computer. And IBM Quantum Platform is free for, like you can sign up for the open plan for free. You can use for 10 minutes of real hardware every month for free. So for example, here I can choose, let's see, maybe I choose this busy job, and I choose this one. Okay, I need to measure. That's a common mistake. So you need to measure it. So I can run this. I choose this one. And it can be very fast depending on the queue. So I don't think we can see the result right now, but okay, let's see. But maybe later, after a few minutes, I can jump back here to see. But basically, this is a very awesome tool for teaching the people that just started, especially if people are not so well versed in coding. So you can already teach them quantum computing concept without like getting the code first. Or even for people that already know coding, they at least don't need to deal with, like, in Python, you need to set up different packages, environment. So all these things might get into the way before you actually want to focus on the concept of like quantum computing. Yeah. Questions?
As an aside, have you used ChatGPT to automate and generate learning activities?
Yeah, so I use so we use different kind of generative AI tools to do this kind of thing. For example, the quiz I mentioned, actually ChatGPT or other tools would be very useful for you to like create quizzes. Like let's say you want to like teach certain concept, and you can tell them like this is the concept and this is your learner background, and create 5 like multiple choices quizzes. In fact, I've used it in the courses I teach, and I put it into Slido, and then yeah, you can tune with that. I think that's one thing that I don't mention in my presentation, but I think we should definitely use more. And especially for the audience that used to hear AI for good, I think that is definitely something AI can do for good. Right? Okay. So moving on. So moving to principle 4 out of the 5. So presenting in multiple ways. So that are different reasons. That okay, principle 1 is learner, right? So you have people from different background, different stages, different goals. That presenting in a different way might help. And also even for the same person, at least I feel it myself. If I'm presenting a different way of explaining the same concept, it just helps me to build up the understanding. Maybe one way to explain, it helps me to get the intuition. The other way to explain maybe have like more like the solid foundation like math, and I feel like, okay, I really grasp how it's actually working. And then visual, sometimes it's just like you just have the impact that you feel, oh, this is how it's working. Like I think using multiple way of explaining it have very good effects for many reasons. So here I give example to explain superposition in 3 ways. So you can use analogy. Maybe the first thing you would do, especially for people who are beginners, so you would say, okay, superposition is like flipping a coin. Before you actually see the land it into a hand, it can be a head or tail at the same time, sort of, because you don't know it yet. So superposition can be a thing of the same. Of course, not exactly the same. So you can help them to understand that there's something like in between states. But then there's also a drawback that maybe you have to say the caveat, okay, how this is not quantum, while quantum superposition is a bit different but similar. And you can explain in math, like if you can show some vector, you can say like classical bits, they can represent it in like some vector, column vectors. 1, 0 is like 0 is 1, 0, 1 is 0, 1. And then qubit is just like a linear combination that of these two states. That is like 0 and 1 with some coefficients. So some people might get this kind of explanation better if they are more math major or physics major. Or maybe after getting the coin flip example, they feel like they need a bit more to actually get them convinced this is something actually happening or something that they can grasp. Or you can explain using code. So I can simulate the superposition using Qiskit or the quantum composer I just showed you, that you can put a circuit, put a Halama gate, and then you can show that, okay, by doing this, I create a superposition. You have 50% of the chances of 0, 50% chance of 1. So now again, is some time for the poll. Which of the explanation you prefer? So we can move to the next one. Which of this explanation do you personally prefer? And you can choose multiple ones. Hopefully that is allowed in this poll. Do you prefer explain superposition through the analogy, or explaining through math, or explaining through code? That is for yourself when you're learning, or maybe you used to learn when you are new to quantum computing. Okay, some people prefer coin flip, some people prefer math. Okay, we have superposition of 3. You equally 3. Nice. Okay, so coin flip wins slightly, which really shows that this very diverse. Like people may prefer a different way, or maybe you find that all 3 is useful for you to understand in a different aspect of the same concept. So lastly is principle 5, show the math, and I think I emphasized many times. And that is because quantum is so weird, like the concepts are so counterintuitive. It's very hard for you to draw your like daily experience, to internalize and feel like you get it, and like for your learners, say. So while the analogy or something that is like games that might help you to draw the first like attention of your learner, or make them feel cool or wow them, I think it's very important that you don't hide the math, because explaining through like simple math and actually will really create meaning. Like they will feel that working through the math, they're starting to really understand how this works. And if you do that from the beginning without scaring them too much, then that is how you actually make someone from like beginner to someone more advanced. Because once they accept that the math and you create intuition, then they feel more confident, even when later there's more weird phenomena. As long as they feel okay, they can go back to math and do some kind of calculation, walking through the derivation, then they will feel this feeling of like getting it. So this is another example. So how do you explain why applying the Hadamard gate twice will bring the qubit back to the original? So you start from 0, you apply Hadamard gate, it becomes 0 plus 1. You apply again, you become 0 again. So you can explain it without math, or you can say using a coin flip example analogy, but using it a bit different way. You can say, okay, Hadamard gate is like creating, when you apply it, it creates superposition. And then the second one, we just kind of undo it. It's like flipping a coin, you change from head to tail, and then flip again, head to, like tail to head again. But it's like very hand wavy, and maybe people say, okay, but so you feel like they might be wondering why like still don't know why this happened. It feels just like magic, like black box. And this is something that I actually often fall into a trap. Like I like to prefer teaching through code, and I often teach people like saying, okay, this is the theory, but you don't need to really care about it. Like let's look at the code, and this is how it works. Then people will feel like, okay, I can run a code like this, but I still don't get it. So I think having math is really helpful, but maybe you can simplify it down to a small example, a simpler one that they feel they can derive, rather than a real world example that might be bigger or more complicated, then they feel like it's out of reach. So for this example, it's very simple, so we can walk them through, okay, Hadamard gate can be described by the Hadamard matrix, and you can say, okay, first you can apply the Hadamard gate, then you change from 0 to 1 over square root to 0 plus 1. Parsing the second one, you can just expand them. Like you just add the second Hadamard gate to the state that you have. And the Hadamard gate applied to the first 0, you become 0 plus 1. And the second one to 1, it will be 0 minus 1. And then you combine these factors, become 1 over half, and you combine the 2 0, and the 1, you see that the coefficient adds up for 0 state, and the coefficient cancel each other to 1. And that's how you end up with 0. And if you explain this way, hopefully they'll feel that this is how it works. It's because interference kind of be like the same state, the 0 state is getting enhanced, while the 1 state is got cancelled. So then that's why you go back from 0 to superposition and then back to 0. So hopefully this kind of simpler math can help your learners to build the foundation that is needed for understand even more complicated concept later on. So we already talked about all these 5 principles. So I want to give you an example and then how we can apply these 5 principles for a concrete example. And you can do this same kind of exercise for the people you are teaching. So this is the template. Like you're teaching certain concept to some learner who wants to do a certain thing. Why are they learning quantum? So I give example. I want to teach a very complicated concept, error correction. And I want to teach to telecommunication engineer because we are working with ITU and who wants to understand quantum computing for curiosity, just for. Is there a question, Jenny?
Yeah, so question in the chat. Do you believe it's possible to achieve a meaningful understanding of quantum principles without deep math, especially for people working in non-technical contexts like government or policy?
Yes, of course, it is possible to learn it without math. Yeah, I understand that there's some people, yeah, I think this example is very good, like government policy, like understanding the impact, or maybe some business owner like C-suite. So for those people, maybe there will be a different way. This may not apply to them. So always get back to principle 1 if you are in doubt, learning, like knowing who you are and why they're doing this. I think that's why in this template also, the goal matters, even if their background is a certain way. What are they trying to do? So for like policymakers, maybe they want to understand is whether they should create some policy to encourage like development of research, or maybe create some special funding scheme for company or something. Then for them, maybe they don't need to care about this math, right? But how do they know the importance of this? Then they maybe, I think it would be helpful if they know at least to, like, how do you read, like maybe some papers or maybe something like reading beyond the news probably is something these people should learn. And how to do that, I don't know. It's hard to give a recipe, I guess. But I would say that reading beyond the news probably is like, don't just read news. Read maybe some more technical, right, review paper, or read something that is more like written by someone that expert. But in any case, I think those will rely on some kind of like a sort of like a secondhand information. So I guess they can also try to see some of these educational resources that they can see, like what are potential applications of this. Like maybe instead of watching some more like marketing videos of the impact of quantum, maybe they can go to, let's say, our Qiskit YouTube video, or something that are geared towards more like educational purposes rather than business purposes. And through that, if they can understand, usually we also explain the impact of quantum, but maybe we explain in a way that is more educational context, then we'll be hopefully remove more of this hype. I think that might be an approach. So for them, I guess, yeah, they wouldn't have time to understand the math. But hopefully the basic math, if they understand and maybe they help them to get convinced. It's hard to say. Yeah. I don't have a good answer, I think. Okay. All right, we still have 5 minutes. Hopefully I'm done with this example, but very good questions. So I'm trying to go through this example. So I'm going to teach a quantum error correction to a telecommunication engineer who wants to understand quantum computing just for curiosity, for like hobby, want to know, they're curious. So the bar is very low, like they don't want to use this for their work or whatever. But the key is that you're learning a very complicated concept and they are telecommunication engineer. So if you apply this leaps principle, first thing is learn. So for telecommunication engineer, hopefully they know the classical communication, then there's classical error correction code, and they understand like this communication channel often have noise, and I think signal processing and those redundancy. Hopefully those things are very familiar to them, but maybe they don't know about qubits and all the quantum concepts. And if using the second principle, explaining through or examples through the scaffolding, is how to build up this from what they know, which is more classical. Then you can build some classical error correction or like majority voting, encoding 1 qubit into 3 qubit. Then they will understand this one. And then moving to quantum, you can do something similar, but the catch is that in quantum you have no clone theorem. You cannot just copy and read out all of them. So you explain those things and give an example that is repetition code for 3 qubits. And instead of like reading out all three, you need to do some parity measurement that can compare the qubit without actually measuring the qubit and therefore destroying information. So then you can explain those concepts to them. And then the other principle is going to enhance this scaffolding way that you're trying to explain. For example, you want to increase active engagement. When you are teaching or whatever, make sure every single step or the way you explain that you ask questions to check or do a quizzes to make sure they're understanding this. Or you can do a Qiskit demo, like at the end, you build a phase flip code or this repetition code or a 9 qubit short code. And presenting in multiple way is also trying to enrich this way that you can teach for analogy. You can use this one or some other way the classical error correction work, like putting multiple hard disks together from a RAID systems, or you put like visuals, how you actually do the encoding in quantum circuits by building this error correction code, and then how to implement these things in Qiskit. And showing the math is to enhance this part as well, to really walk through them why this works. What happens when a bit flip error happens, and how when you do like parity measurement, you can detect the error and also correct the error. So this is a very simple example, and you can try to think about the same example for the people you're teaching, and maybe your learner have multiple background. You can try to do multiple of these exercises and find out maybe there's a way that you can try to adopt to all these people. So that's a summary. Teaching quantum is hard, so it's not because you're no good, it's just very hard because they're very non-intuitive and there's people from different background. And to learn that, people need structure, engagement, and clarity. And so that's how I come up with this. And hopefully, if you forget everything, remember these 5 things. I make up this acronym just so that you can remember them. And obviously, it doesn't it's not completely make sense like how I put this, but it's just for memory. So learner first, examples and scaffolding, active engagement, present in multiple ways, and show the math. And I also show you some tools that you can use. So yeah, with that, I think that's the end. Yeah, so in IBM Quantum, we provide a lot of learning resources, and we also host a lot of events that can be useful for you and also your learners. You can use the learning platform. There's a lot of courses. You can use the Qiskit YouTube channel. We have a lot of educational videos, and we have a lot of events, IBM Quantum Challenge, Qiskit Global Summer School, Qiskit Fall Fest, and also Quantum Developer Conference. And you can go to follow the IBM Quantum LinkedIn, and you should be able to receive the updates of these events. So with that, I'm happy to take more questions if there are any, and you can find me on LinkedIn. Right.
Right, I'm just monitoring the chat, but it seems like all the questions have been asked. Let's say thank you, Junyi, for this great talk. I hope people gain valuable insights on how they can approach teaching quantum. And thanks for everyone for tuning in. Hope to see you at the next workshop. Thanks again,
Thank
Junyi.
you.
Thank you for participating in today's AI for Good session. We hope you've learnt something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for good.